In this video, we will write a CUDA program using the C programming language to add two vectors. I'm using Visual Studio with the Nsight plugin, which was installed with the CUDA toolkit. To start, we create a new CUDA project, which you can do by selecting the CUDA template from the Visual Studio template library. By default, a CUDA project contains a kernel file with sample code. We won't be using the sample code, so let's replace it with CPU-only code that adds two vectors. Let's look through this code now. The main function allocates three variables, A, B, and C. The variables are initialized in a for loop, and after initialization, the vector add function is called. In the vector add function, we add the elements of vector A to the elements of vector B and assign the result to vector C within a for loop. Back in the main function, the resulting vector C is printed and the memory is freed. Now let's compile and run this example. It prints out the first few elements of vector C. Note that even though this is CPU-only code, it can be run in a CUDA project. Now let's parallelize this function to execute on a GPU. This has three steps. First, make the variables accessible to the CPU as well as the GPU. Second, specify the launch configuration of the kernel function. Third, parallelize the kernel function to run on a GPU. So first, let's make sure that our variables are accessible to the GPU. To do this, I allocate my variables using the function CUDA malloc managed. This command places our variables in a memory space called unified memory that is available both to the GPUs and the CPUs in a system. CUDA malloc managed returns a pointer that you can then access from host and device code. To free data in unified memory, pass the pointer to the function CUDA free. Next, let's update the function called vector add to specify the launch configuration of the kernel. To do this, we will use triple angle brackets. The first parameter in the triple angle brackets is the number of thread blocks, which in our case, for simplicity, we'll only use one block. The next parameter is the number of threads within each thread block. In our case, we will set that number to the number of elements in the vectors, which is 1024. This way, each instance of the kernel will launch in an independent thread. To ensure that the CPU waits for the kernels to complete before continuing, use the command CUDA device synchronize after the kernel launches. Finally, let's parallelize the vector add function. So add the keyword global to the function definition. This tells the compiler that this function will be executed on the GPU and is callable from the host. This function will be run by many threads in parallel. So to identify each thread, we can use a read-only variable called threadIDX within it. ThreadIDX is unique within each thread. And since each element of the vector is now being independently executed, we do not need to loop through using the for loop anymore. However, we should use an if check to limit operations on the number of elements in the array. This way, even if we were to launch more threads than the elements in the array, we should not have a problem. Now build and run the application. And we can see that the result is identical to the one with CPU-only code. And that's it. We've now written a function in the C programming language that can execute on the GPU using CUDA.